Well, thank you guys for sticking with me. Look at all you people. All right, let's do this. So, okay, this is an incredibly exciting talk about fragmentation, so I'm very impressed that so many people came. But let's get into it. Let's see if this works. Did it work? I hit a button. Did it do anything? Did not do anything. Hit this button. There we go. All right. So this talk is about fragmentation. And the reason I am giving this talk is because in Ceph, I'm going to assert right now that fragmentation is actually one of the biggest causes of performance problems that we have seen over the last 10 years. So it can happen in a lot of different places. We see it in object data, we see it in metadata, we see it in free space, and we see it even in memory. And this isn't really unique to just Ceph. This happens on all kinds of different storage systems, many different file systems, and in even like key value stores. So I wanted to ask folks here, how many of you were around in the FileStore days? Let's get like a raise of hands. Quite a few, not everybody, but quite a few. So I'm going to give just a little bit of background on what things were like back then. So FileStore always wrote data out to a journal. One of the kind of its key things is that it didn't just write out like metadata like you see in some file systems, like you see with BlueStore today, but it actually wrote out data to both a journal and to the disk asynchronously later, but you did see like seeks jumping back and forth. Another thing I wanted to mention is that in FileStore, objects were written out as files on a file system, like a POSIX file system, so XFS, Btrfs, whatever. The way that was laid out was very interesting. I'm going to get into this a little bit later, but the big thing to know is that the files that were stored were laid out in a nested directory structure, and some of the metadata, not all of the metadata for an object, was stored in X-adders. And to grow the amount of objects that were in a FileStore, that directory structure was periodically grown and became larger and deeper and wider. So just kind of keep that in mind as we go through this. Next. All right, so there's a couple of things, like just a couple of examples I want to give you guys to think about as we go through this talk. So in the FileStore days, this is an easy one, it's a very straightforward one. When you were running on top of XFS, XFS stored some of the Ceph metadata in X-adders in the inode. And back in those days, you'd set the inode size when you created the file system. So typically for Ceph, we used like 2K. And this worked great most of the time, but if you had very large X-adders, you would actually see that it would have to split that data to fit it. Part of it would go into the inode, and part of it would have to go out into a separate extent on the disk. So right away, if you had too much metadata in FileStore, you would end up doing an extra seek just to go out and fetch metadata before you've even gotten to the data portion of the object. And then in addition to that, whatever data you have, whatever extents that's spread over, you're doing seeks for that as well. So just right away, we had multiple different ways that you could fragment just here alone. Next, in XFS, we saw that when you were kind of growing your object store, when you're putting more data into Ceph, in XFS, they have this concept of allocation groups. And when you would put data, or when Ceph would put data in one directory, it would be put into a particular allocation group that was associated with that directory. But the way that Ceph worked is that it would take a directory that had a bunch of objects in it, and it would create new subdirectories under it, and then redistribute the objects that were in that directory to those subdirectories. But those subdirectories themselves might end up in a different allocation group. And these allocation groups were spread out over the disk. So what would happen over time as you grew and shrank an object store, objects in a directory would end up being spread across the disk. You would no longer have all of the objects in one directory in the same allocation group by each other. They would actually get spread out. And that meant that things like doing an iteration across a directory, like say if you're doing a collection listing, could end up being incredibly slow. This was actually one of the huge, big things that kind of made FileStore not work very well in practice as it grew really large, and one of the reasons that we wrote BlueStore. So the third example I want to give you is one that's going to be really relevant later on in this talk. But we looked at deploying, for a while, FileStore on Btrfs back in the very early days of Ceph. And one of the big problems with Btrfs, with Ceph running on top of it, is that when you, Btrfs is a copy on write file system. When you do an overwrite of some data, it will write that small little overwrite into a different portion of the disk, and then it will remove the old data from the contiguous area where you had it written, and now you've got two separate contiguous areas with a hole in the middle. And as you do this over and over and over again, you can imagine now you've got like all of these holes that get filled in with other little bits of data, and you've got like severe fragmentation. And we observed this. We did performance testing where we looked at doing like sequential writes and then going back and doing sequential reads, and it looked great. But then you go back and do a bunch of random overwrites of that data, and after that, everything was horrible. Performance tanked, looked really bad. So keep this in mind because it's going to be relevant. Okay, so we kind of already talked about this, but the gist of it is all of these problems in aggregate in FileStore caused a lot of problems. It was really, really bad. They weren't always happening at the same time. XFS was a little bit different than Btrfs, but in aggregate, this was bad. So this ultimately led, in part, to why we decided to write BlueStore. So BlueStore works a little bit differently than FileStore does in that a lot of the things that we had in FileStore that we just talked about, like how we map where objects are located and where we place metadata, a lot of that ended up being moved into RocksDB. And RocksDB, I think most of you probably know what it is. It's a key value store. I'll talk about it a little bit here in a bit, but the gist of it is that RocksDB really kind of became the cornerstone for how Ceph stores metadata in the BlueStore era. So the other thing that I wanted to mention too regarding RocksDB usage in Ceph, or in BlueStore rather, is that we use the write-ahead log in kind of as a replacement for the FileStore journal, but we only write metadata to it. We don't do full data journaling. And this was a really huge win back in the BlueStore era because it meant that we no longer would do like a full double write of all data, especially for like large amounts of data. But we still do small like writes for metadata kind of as you're also doing large writes for other things, or I should say rather object writes. So there is still this effect going on to some degree, especially when you have like a shared hard drive. You're using it for both the wall and for objects. So one of the key things that RocksDB does that's kind of important is that it will write data out to the write-ahead log contiguously. It's appends, it's just doing appends. And when those write-ahead log, when the write-ahead log fills up, and specifically when the in-memory representation called memtables fills up, it will flush that data out to the database itself. And as that fills up, when compaction happens, the SST files that basically represent all of the key value pairs that are in RocksDB, those are also written out contiguously. They're written out, and once it's written, it's immutable. It's done until you do another compaction, and then it's writing out new files. So this just kind of showcases what we just talked about here. As compaction happens, we basically move data into deeper and deeper levels. Those are bigger and bigger, but they're always written out contiguously and in sorted order. So this is kind of an overview of that whole process. We have the write-ahead log. We have data coming into the write-ahead log. in BlueStore, that's primarily metadata. There are small deferred writes that happen, but I don't want to get into that right now. And there's this process of basically filling up mem tables, and then once they become full, and we have different kind of criteria for determining when a flush should happen, that data then gets flushed to the SST files in different, like level 0, and then compaction basically takes those and distributes them lower and lower into the database. Okay, so all of this is really great in theory. RocksDB really tries hard to keep data laid out contiguously. But remember that problem with Btrfs that we talked about just a little bit ago? We have the same problem in BlueStore. BlueStore is copy on write, just like Btrfs is. And we can leave holes, we often do leave holes in data when there's small overwrites. It happens especially in RBD, because in RBD you have objects that represent blocks, and when you do small overwrites in that block, probably because maybe you're deleting a file, or maybe you're just editing part of a file, then you can end up with holes, just like Btrfs. So RocksDB has something that kind of looks, if you kind of squint, it looks a little bit similar. In RocksDB, when you're deleting a key value pair, you're not leaving a hole like you do in like Btrfs. Instead, you're inserting a tombstone that basically tells RocksDB that the data is going to be deleted, that it is deleted, but that you're waiting until a compaction happens to actually remove those tombstones and no longer compact that data back into the new SST files that are generated. And that has its own problems. When you accumulate tombstones, when you accumulate a lot of them, because there are a lot of deletes, you end up having to walk over all of them when you're iterating through keys in RocksDB. It's really, really painful, especially when you're doing something like a mixed workload, or a workload where, say, you're iterating over a range to find a key to delete, and then you delete it. And by deleting it, in reality, you're just inserting a tombstone. And then you start over again looking for the next one, and you iterate over the same range, now iterating over the tombstone that you just created to find the next one, and then you're removing that and inserting another tombstone, and you do it again and again and again. And we actually saw this causing heartbeat timeouts, where the OSD got into such a severe state of walking through tombstones like this that it would actually cause the entire OSD to basically go down. So there's an interesting fix for this, and it's not ours, it's actually the RocksDB team themselves that did it, but we didn't have this exposed in Ceph until Pacific. And all this is basically when you are iterating over tombstones, RocksDB can watch it. It can say, I've iterated over so many keys, I've encountered so many tombstones, and at some point you make the decision, okay, now it's actually in our interest to compact. Even though compaction is kind of a heavy process, it's better to do that than it is to keep going through this crazy cycle that we're seeing. And so that's the PR is listed in this talk. You can go look at it if you want. But for any friends from DigitalOcean that are in the crowd, I thank you for providing these ages ago. But this is actually data that they provided us before and after that patch that shows just how dramatic the behavior changed. In this case, they saw increasing latency as they walked over and saw these key value deletions taking place. And after the patch was enabled, it was extremely steady at a much lower latency level. So this was a really huge improvement. And I kind of mentioned earlier, if you squint, it kind of looks like the copy on write issue. They're similar. They're not exactly the same, but they're similar. So one of the things, so actually I have a little bit of sidetrack here, but one of the things I wanted to mention is that RocksDB it tries very hard to keep everything contiguous. But imagine what would happen if you do have this like copy on write fragmentation. You're doing lots and lots of workload, lots of churn, and the SST files themselves that RocksDB is trying to ask BlueStore to allocate space for, if BlueStore is fragmented and if free space especially is fragmented, then RocksDB can't guarantee that its SST files are actually going to be laid out contiguously. It can try, it can request like a block of contiguous space to write its files out to, but in reality, BlueStore might not be able to do it if the underlying system is fragmented. And I wanted to point out another PR here that actually Igor wrote, and he couldn't be here today, but I wanted to make sure he got credit for this. He noticed that we were actually not pre-allocating space for RocksDB. So what happened is that RocksDB would request space just like anything else in BlueStore, and over time, as things got fragmented, RocksDB SST files would become fragmented, and then that led to even worse problems. So what I was trying to get at earlier was that what they're doing in RocksDB kind of provides us with a little bit of a hint about what we can do for the issue that we still have in BlueStore regarding fragmentation. Every time that we have to read an object, we iterate over all of its extents, basically all of the different places where we store data on the disk. And for very fragmented objects, this is painful. It takes a long time, especially on hard drives. Even on NVMe a little bit, because there's still a lot of overhead, even though the NVMe drive can basically seek more or less for free, there's still a lot of CPU overhead to doing this. So you can kind of think about it, if you're going through all of that pain anyway, the cost of actually rewriting the object out is relatively small. It's not that bad. If you're reading over like a couple dozen extents, you're gonna already be paying the pain or feeling the pain just doing that. So as long as you have contiguous free space, you're probably better off actually writing out the object again in a contiguous form. So there was an interesting use case a couple of years ago where we had an opportunity to try it. So I don't know how much you guys remember or if anyone had this issue, but RBD mirroring was pretty slow for a while. And the reason it was pretty slow was because when it adopted using clone, basically RBD snapshots. So what we noticed is that when you are doing a clone operation and you're iterating over all of the blobs in BlueStore, which are basically just kind of a different data structure, but you can really think about it more like kind of iterating over all of the extents, because that's kind of part of it. It has to spend a lot of time doing that iteration to be able to perform the clone operation. And it was really quite, had quite high overhead, both in terms of CPU, and it was not particularly good in terms of performance. So Adam Kupchak and I were both discussing this, and we decided to try different approaches to solving this. Adam Kupchak wrote all of the Elastic shared blobs code, which some of you may know about. And it's really impressive. The design behind it is very ambitious, but it solves this in a really good way. The approach I took was comparatively very lazy. I basically looked at, okay, on clone, can we just look at how many extents there are in the object and say, okay, if it's really like heavy, let's just like defragment it and then like go on our merry way. This has downsides. When you do that, actually you increase the amount of data that's required to be stored for doing snapshots and for the RBD mirroring process. But, there we go. But it kind of worked. It was not bad. Like, you can see the original is this blue line. The defragment on clone approach that I took is the green line. And then Adam's work is the Elastic shared blob code, which is the pink line below it. So here's just kind of the overview, kind of a high-level view of the performance that we saw in each case. you can see that like defragment on clone got us kind of like halfway between where elastic shared blobs ended up and the default in Quincy for spikes specifically. It was not quite as good when just looking at the average CPU usage, so it was better at bringing the spikes down, but didn't fully help there. But the big thing, and I tease Adam a little bit about this, I teased him a little bit before this presentation, the elastic shared blob code ended up adding like 4,000 lines of code, removing about 700. The defragment on clone was like 50 lines of code, it was tiny, right? But having said that, all of the advantages that the elastic shared blob code had really makes it like worth it. If it's stable, if we can use it, it's the better way to go for this problem. All right, so let's see. Yeah, I kind of went over most of this already. I'm really bad about reading it, like saying what's in the next slide and then having nothing to talk about. But right. Okay, so we went with elastic shared blobs. I think that's obvious to everyone. But what I wanted to say is that defragmenting objects like this is still really valuable. I think even outside of cloning is still really, really important. And what we started to think about was, okay, if not clone, what's the place to do this? Where should we be doing this? And especially, where are we already reading large numbers of objects, paying that pain to iterate through all of the extents, and where can we then basically clean them up? And the answer is deep scrub, right? You're already iterating through all this stuff. Deep scrub is already like affected very painfully by the fact that you're iterating over fragmented objects. And if you're doing that anyway, rewriting it is not that bad. And then the next the next deep scrub you're going to do is going to be way faster because of it. So it's worth paying that little bit of extra pain to do the write to clean it up. There are corner cases, right? Like if your free space is fragmented, what happens if you try to rewrite the object and it's just as fragmented as it was before you did it, right? You could end up just endlessly rewriting objects and it'd be terrible. So there's choices to be made there. Do you only defragment when you have contiguous free space that you can write into? Do you do it if you can make it less fragmented but not perfect? These are kind of things that we were thinking about. So one of my colleagues at Clyso took a stab at this and actually implemented a PR that's been sitting for a little while. We need to get back to it, but it's there, that defragments on scrub. And we asked ourselves, once you're defragmenting on scrub, what else could you do? And in addition to defragmenting there, we're also now looking at an object and trying to determine, can we compress it at the same time? Can we both defragment it and compress it, take an existing pool that has basically no compression on it, and can we then later decide that some of that data should be compressed, maybe not all of it, maybe some of it we leave uncompressed. But that's the first draft of that implementation is here with discussion, and for anyone interested, I'd definitely love to hear feedback on it. There are a lot of unexplored topics here that I didn't get into this talk because I figured I couldn't get them in, but there's so much interesting that's going on. Memory allocation and fragmentation. This is a huge topic, and we see it all the time in Ceph. We make tons of little memory allocations, and we can, I think, do quite a bit better. BlueStore's DENK framework. This is basically a first attempt at solving that problem. Initially in BlueStore and in other parts of Ceph, we will go through and allocate memory, basically data structure by data structure. And DENK lets you basically walk through deeply into data structures, figure out how much memory is needed, and then do the allocation in one go. There's trade-offs between defragmentation and deduplication. These are really important topics that haven't really been discussed a lot, but it's there. CStore is going to handle fragmentation very differently than what we do right now in in BlueStore. So that's also a big thing. And then there's like a whole separate talk that could be given just on tools for detecting and analyzing all of this behavior. So I wish I could have gotten into them, but not for today. but would be happy to talk about it with anyone that wants to. That is the end of the talk. I have no idea if I went over. Let's see. How bad was it? All right, am I supposed to, like, are we doing questions or am I done? Okay, oh, good. So, yeah, please go ahead.
Can you point us to where we could find some tools for analyzing the fragmentation?
Yeah, sure. There is a fragmentation score that you can get from the OSD. I don't know how good the documentation is for it right now, but it's there. So I'll talk to Anthony, and maybe we can make sure that that's in good shape. But there is that. I also really like a couple of different tools for looking at it on the device itself. There's a tool that was written by Chris Mason many, many years ago that will take block parse output and then show you a movie of how things are being written out to the underlying device. So that is, in the old days, it was called SeqWatcher. Now it's called IO Watcher. And that will take block parse data and give you a nice visual representation of it. Otherwise, things like IOStat are very useful for looking at just how IOs are being merged and what sizes they are and all these kinds of things. And then if you really want to go crazy, you can actually enable like debugging at the BlueStore level, like high-level debugging, and see like way more data than you ever want to. So hopefully, does that answer?
Yeah, thanks a lot. Those are good tips.
Yeah. Yes, yes. Good call, Alex. Or,
Fragmentation histogram.
Yeah, was that Igor's, Adam? Yeah, it was Igor's work. So another very good contribution from Igor. All right.
I can try one here. For the fragmentation, have you tried different allocation units on the low level? Because when you do 4K, your tendency to fragment is higher. So if you get higher allocation units, you...
Yes, there was a lot of discussion about 5 years ago when we decreased the default allocation unit, or so the min-alloc size on hard drives from 64K to 4K. That, of course, showed really, really bad results when we made that change initially. Not in production or anything, or for the Ceph code base, but when we were starting to explore and play with that. And here I can mention Igor's name again. Igor did a ton of work back in those days to look at how we could try to minimize that as much as possible when we drop down to that 4K min-alloc size. It's not perfect. We still see, I think, more fragmentation, especially over time, than we did when we had the 64K min-alloc size. But there are trade-offs, right? So
yeah, because it's a fragmentation on the file level is about the inodes. Right?
Yeah.
So you want to tend to get that less, and physically you cannot see on the device. So if I look at the device per se, I cannot tell if it is fragmented or not, because that's how we just write data. We don't know the structures.
Yeah, and one of the interesting things there too, right, is if you've got a 64K min-alloc size, you're actually putting less data in RocksDB as well, because you have fewer metadata structures that you need to store there. So going down to a 4K min-alloc size had definite trade-offs. Like, it's good and it's bad all at once. All right, are we done? I think that's probably about time. Unless there are any last-minute questions. All right. Well, thank you very much, guys. Really appreciate it.